Voyager 1 is currently moving through a region of space where the temperature of the surrounding medium hovers just above -270 degrees Celsius. That is 1 degree above absolute zero. The theoretical floor, where all atomic motion stops and matter reaches its lowest possible energy state. The spacecraft is over 23 billion kilometers from Earth. It crossed the edge of our solar system more than a decade ago. And right now, in 2026, it is still transmitting, still functioning, still talking. That fact alone deserves a moment of pause. Because what it implies about both the engineering decisions and the nature of cold in deep space is more counterintuitive and more fascinating than most people expect. Assumption most people carry around is that deep space is a lethal freezer, that any machine sent into that environment would crystallize, shatter, and go dark within years. That assumption is wrong, but not because space is warm. It is wrong because of something far more fundamental. Cold in space does not work the way cold works on Earth. Understanding that difference is the first key to understanding how Voyager 1 is still alive. When you step outside on a cold winter morning, what you are experiencing is not actually the absence of heat. You are experiencing a very specific physical process. Air molecules, numbering in the billions of billions per cubic centimeter, are colliding with your skin at high speed. Each collision transfers kinetic energy away from your body. Your skin is hotter than the surrounding air, so the net flow of energy runs outward from you into the atmosphere. The faster and more densely packed those air molecules are, the faster you lose thermal energy. This process is called conduction, and its defining requirement is contact. It needs matter. It needs particles. It needs a medium through which energy can travel by direct molecular collision. In the interstellar void, where Voyager 1 currently travels, there are roughly 1 to a few atoms per cubic centimeter. Compare that to the air in a typical room, where you have approximately 2.7 times 10 to the 19th power molecules per cubic centimeter. That is 27 million trillion molecules per cubic centimeter. The interstellar medium has perhaps 2 or 3 atoms in that same volume. The ratio is so extreme that it becomes almost meaningless to express as a comparison. The interstellar medium is not thin air. It is essentially the closest thing to true vacuum that exists in nature, with so little matter present. Thermal conduction is reduced to near zero. There is nothing to collide with. There is no mechanism to strip warmth from a spacecraft the way winter air strips warmth from an ungloved hand. And this changes the entire physics of survival in space. If conduction is gone, how does heat escape? Through radiation. Every object with a temperature above absolute zero emits electromagnetic radiation, specifically in the infrared portion of the spectrum. This is not light you can see, but it is energy leaving the object in the form of photons traveling outward in all directions at the speed of light. In a vacuum, radiation is the only mechanism by which heat can move. There is no conduction because there are no particles. There is no convection because convection requires a fluid medium. Only radiation remains, and radiation, critically, is slow. It is gradual. It is manageable. Think about what this means. Imagine placing a cup of hot coffee in a cold room. Within minutes, the coffee loses heat rapidly because the surrounding air is constantly in contact with the ceramic mug, conducting energy away. Now imagine sealing that same cup in a perfect vacuum. The rate of cooling drops dramatically. The only way heat can now escape is by radiating outward as infrared photons. The coffee stays hot far longer. Voyager 1 is that cup of coffee, floating in a vacuum so profound that its heat can only escape through radiation. If it generates enough heat internally, and if it is insulated well enough to slow that radiative loss, it can stay warm enough to function indefinitely, or at least for decades. But generating heat in deep space requires solving a problem that engineers at NASA confronted very deliberately in the early 1970s. You cannot use solar power, not at those distances. At the distance of Jupiter, sunlight is already 25 times weaker than it is at Earth. At the distance of Saturn, it weakens further still. By the time a spacecraft has crossed into interstellar space beyond the helium, sunlight has dropped to essentially nothing, less than 1/10,000th of its intensity at Earth. Solar panels, capable of generating useful power at those distances, would need to be enormous, far heavier than any mission, budget, or rocket could accommodate. And even then, they would only work for the early portion of the journey. They are a non-solution. The engineers chose plutonium instead. Specifically, they chose plutonium-238, a radioactive isotope with properties almost uniquely suited to long-duration space missions. Unlike plutonium-239, the isotope associated with nuclear weapons, plutonium-2-3-8 decays primarily through alpha emission rather than fission chain reactions. Alpha decay releases heat at a steady, predictable, and continuous rate. It cannot be switched off because it is not a chemical reaction or a mechanical process. It is a fundamental physical property of the atom. The nucleus of plutonium-238 is inherently unstable. It will decay. That decay is inevitable and consistent. Voyager 1 carries 3 radioisotope thermoelectric generators, often abbreviated as RTGs. Each is a self-contained unit containing plutonium-238 dioxide ceramic pellets surrounded by heat converters. The decay heat from the plutonium flows through thermoelectric materials, substances that generate an electrical voltage when one side is maintained at a higher temperature than the other. This is known as the Seebeck effect, named after the German physicist Thomas Johann Seebeck, who first observed it in 1821. When you apply a temperature gradient across certain semiconductor materials, electrons migrate from the hot side to the cold side, creating an electric current. In an RTG, the hot side is heated by the plutonium decay. The cold side radiates heat into space. The temperature difference drives a steady electric current. There are no moving parts. There is no fuel that burns up. There are no switches to flip. There is no maintenance to perform. The system operates entirely on the quantum mechanical inevitability of radioactive decay. When Voyager 1 launched in 1970, its 3 RTGs together produced approximately 470 watts of electrical power. That is roughly enough to keep 4 or 5 incandescent light bulbs lit by the standards of modern computing or consumer electronics. That sounds absurdly low, but Voyager was designed to be extraordinarily efficient. Every scientific instrument, every transmitter, every circuit was engineered to operate on a shoestring of power. The spacecraft weighed 815 kilograms at launch, but its electrical budget was the size of a modest desk lamp. The RTGs served a dual role that is often overlooked when people discuss Voyager's power system. Yes, they generated electricity, but they also generated heat. And in the cold of interstellar space, that heat was as vital as the electricity. The warmth from the RTGs conducted through the spacecraft's structure, keeping cables, circuit boards, gyroscopes, and instruments within their operational temperature ranges. Every electronic component that fired, every microprocessor cycle that ran, produced its own small contribution of residual thermal energy. The spacecraft's interior became a self-warming system, a closed thermal loop in the middle of an infinite cold. But heat alone is not enough if you cannot hold on to it. You need insulation. The challenge the engineers faced was not simple. They had to design a thermal protection system that could handle two completely opposite conditions. In the early years of the mission, Voyager was relatively close to the Sun. The RTGs were producing peak power. The electronics were generating heat, and although sunlight at Jupiter's distance is far weaker than at Earth, it was still a thermal input the spacecraft had to manage. Overheating was a real concern. The thermal system had to be able to shed excess heat when needed. But as the decades passed and now the challenge was holding heat in, preventing the slow radiative loss of thermal energy into a medium that was 1 degree above absolute zero. The solution was multi-layer insulation, or MLI. This technology consists of ultra-thin sheets of mylar and Kapton polymer film, layered together with tiny glass or plastic beads or fabric spacers between them. Each layer is extraordinarily thin, sometimes only a few micrometers. The layers are not bonded together. There are microscopic gaps between them, gaps that are close enough to vacuum to prevent conduction. Each reflective layer bounces infrared radiation back, reducing the net outward flow of thermal energy. Stack enough layers together, and you create a thermal barrier that slows radiative heat loss by orders of magnitude. Voyager is wrapped in this multi-layer insulation like a gift sealed in the most sophisticated packaging ever conceived. The material is so light, it weighs almost nothing. It is so thin, it is nearly invisible. But its thermal performance is extraordinary. The spacecraft also incorporated thermal louvers, mechanical shutters, similar in concept to Venetian blinds. When the spacecraft was too warm, the louvers opened, allowing excess heat to radiate away. When the spacecraft needed to retain heat, the louvers closed. This allowed active thermal management without requiring any electrical power for heating or cooling elements. The louvers are mechanically operated by bimetallic strips that respond directly to temperature. No computer, no control system required. Pure, passive engineering, and it worked. For nearly half a century, across a journey from Earth to the very edge of solar wind influence and beyond, the thermal system maintained Voyager's core electronics within their operational ranges. In August 2012, Voyager 1 crossed a boundary that no human-made object had ever reached. It passed through the heliopause. The heliopause is the outermost boundary of the heliosphere, the vast bubble of charged particles, magnetic field, and solar wind that our sun projects outward in every direction. Inside the heliosphere, the solar wind, a constant outflow of protons, electrons, and alpha particles streaming from the sun at speeds between 300 and 800 kilometers per second, dominates the environment. The solar wind pushes outward against the interstellar medium, the diffuse gas and plasma that fills the space between stars. Where these two pressures balance, where the outward push of solar wind equals the inward pressure of the interstellar medium, you find the heliopause. Scientists had been predicting where this boundary might lie since the 1950s. Voyager 1 gave us our first direct measurement, and the data it sent back were surprising in several ways. The transition was not a sharp line, but rather a turbulent, fluctuating region. Voyager actually appeared to cross back and forth across the boundary multiple times in 2012, before finally exiting the heliosphere for good. The boundary oscillates, it moves, it breathes with the solar cycle. When solar activity is high and the solar wind is stronger, the heliosphere expands. When solar activity is low, it contracts. Voyager 1 happened to cross during a period of this natural oscillation. Once outside the heliopause, the environment changed in measurable ways. The rate of solar wind particles detected by Voyager's instruments dropped to essentially zero. The magnetic field orientation shifted, aligning more closely with the direction predicted for the local interstellar magnetic field rather than the direction influenced by the sun and the intensity of galactic cosmic rays. High-energy particles originating from supernova and other energetic events throughout the galaxy increased significantly. Inside the heliosphere, the solar wind and magnetic field provide partial shielding against these cosmic rays. Outside, Voyager was exposed to the raw, galactic environment. One of the more counterintuitive facts about the interstellar medium concerns temperature. The plasma in some regions of the heliosphere can be at temperatures of millions of degrees Celsius. That sounds impossibly hot. But temperature in this context refers to the average kinetic energy of individual particles, not to the ability of that plasma to transfer heat to anything. The plasma is so sparse that even at millions of degrees, a spacecraft passing through it gains almost no thermal energy. There simply are not enough particles to deliver meaningful heat. The spacecraft's thermal experience is determined almost entirely by its own internal heat sources and by radiative emission, not by the surrounding medium. Beyond the heliopause, the interstellar medium is cooler and denser than the heliospheric plasma. Cooler in the sense that individual particle energies are lower, denser in the sense of slightly more atoms per cubic centimeter, though still vanishingly thin by any terrestrial standard. Voyager crossed into this region and continued. The RTGs kept producing heat. The multi-layer insulation kept trapping it. The thermoelectric generators kept converting it into electrical power. And the transmitter kept sending signals back to Earth. Signals that now take over 22 hours to reach us, traveling at the speed of light, 299,792,458 meters per second, across more than 23 billion kilometers of essentially empty space. But nothing lasts forever. Plutonium-2-3-8 has a half-life of approximately 87.7 years. Every 87.7 years, half of the remaining plutonium atoms have decayed into uranium-234, the product of alpha decay. As the plutonium decays, the heat output drops. And as the heat output drops, the electrical power available to Voyager's systems diminishes. Since launch in 1977, the RTGs have lost roughly 40% of their original power output, from 470 watts at launch down to approximately 250 to 260 watts today. The decline is slow but relentless. It drops by approximately 4 watts every year. NASA has been managing this power decline with extraordinary precision and deliberateness. Over the decades, they have systematically powered down systems to keep the most critical instruments alive. The cameras were turned off long ago, their power budget reallocated to instruments more valuable in the interstellar medium. Certain science instruments were deactivated. Heaters for non-essential components were switched off, allowing those components to cool to temperatures below their original operational specifications. As long as the core systems, the transmitter, the science instruments, and the computers that process and encode the data remain within functional ranges, mission controllers are willing to sacrifice peripheral systems. It is a managed decline, calculated, deliberate, and inevitable. Engineers at the Jet Propulsion Laboratory in Pasadena, California, have been essentially triaging a spacecraft across interstellar distances, deciding in real time which systems live and which are allowed to go cold. Current estimates suggest that the last science instruments will go silent somewhere between 2025 and 2030. As of 2026, some instruments may already be offline. The timeline is driven not by hardware failure in the traditional sense, but by physics. The plutonium is decaying. The heat output is falling. The electrical power is dropping. And eventually, there will not be enough electricity to maintain the transmitter. When that moment comes, Voyager 1 will not explode. It will not be destroyed by a collision or a radiation burst. It will simply go quiet, one instrument going dark. Then another. Then the transmitter itself. One final signal crossing over 25 billion kilometers of empty space, taking more than 23 hours to reach Earth at the speed of light, and then silence. But here is the aspect of this story that most people do not fully appreciate. When Voyager 1 goes silent, it does not stop. In the absence of air resistance, in the absence of any frictional force, in the vast emptiness of interstellar space, there is nothing to slow it down. Newton's first law of motion, stated in 1687, says that an object in motion stays in motion unless acted upon by a net external force. In interstellar space, there are essentially no net external forces acting on Voyager at the scales relevant to this discussion. The gravitational pull of distant stars is real but extraordinarily weak at these distances. Voyager 1 is currently traveling at approximately 17 kilometers per second relative to the Sun, that is over 61,000 kilometers per hour. It has been traveling at roughly this speed since it completed its planetary flybys and received its final gravitational boost from Saturn's gravity in 1980. It will continue traveling at approximately this speed, essentially forever, in roughly 40,000 years. Voyager 1 will make its closest approach to a star other than our Sun. The star is Gliese 4, a small red dwarf located in the constellation Camelopardalis. approximately 17.6 light-years from Earth. The approach will not be a collision. Voyager will pass at a distance of approximately 1.6 light-years, still an enormous distance. But it will be the nearest any human-made object will have come to another stellar system. There will be no signal to record the moment. No instrument will be active. No antenna will be pointing at Earth. Voyager will be a frozen, silent piece of metal drifting past a star it has been traveling toward for 40 millennia, and no human alive today, no human alive within hundreds of generations from today will witness it. Onboard Voyager 1 is the Golden Record, a 12-inch gold-plated copper disc containing sounds and images selected to represent life and culture on Earth. The record includes greetings in 55 languages, musical selections from around the world spanning traditions from Bach to Chuck Berry to a Navajo night chant, sounds of Earth including rain, ocean waves, bird calls, and a human heartbeat, and 115 images encoded as analog signals, including photographs of humans, landscapes, scientific diagrams, and city scenes. The record was assembled under the direction of Carl Sagan and was intended as a message in a bottle cast into the cosmic ocean. A greeting from a small, curious species to whoever or whatever might one day encounter this artifact drifting through interstellar space. The probability that any other civilization will ever find Voyager is, to be honest, vanishingly small. The distances involved and the timescales required are nearly incomprehensible. Even after 40,000 years of travel, Voyager will have covered less than 1 light-year, a fraction of the distance to even the nearest star system, Alpha Centauri, which lies 4.2 light-years away. The interstellar medium is vast. Finding a single small spacecraft in it would be like finding a specific grain of sand in all the oceans of Earth. Without knowing which ocean, without knowing which hemisphere, without being able to search faster than the speed of light. But the record is there. It travels. It endures. The copper disk will not decay significantly for billions of years in the absence of chemical corrosion. The information encoded on it remains readable to any civilization with sufficient technical sophistication to decode an analog signal. Whether it will ever be found is unknowable. But the fact that it was sent, that a species still in its technological infancy took the time to include a message of greeting in a spacecraft they knew would travel beyond their own solar system, says something profound about the nature of human curiosity. Let us return to the physics, because there is more to understand about how Voyager has survived, and what the limits of that survival actually are. The multi-layer insulation that wraps Voyager was not pulled from a shelf. It was engineered specifically for this mission. The challenge of thermal management in space involves balancing two competing requirements. The insulation must be light enough to contribute minimally to the spacecraft's launch mass, because every gram launched to space costs enormous amounts of energy. But it must be effective enough to maintain the temperature gradients required for the instruments and electronics to function. The reflective polyester film used in MLI blankets was developed in the 1950s by DuPont and first used in space applications in the early 1960s. Kapton, a polyimide film developed by DuPont in the 1960s, was chosen for its extraordinary stability across temperature extremes. from minus 269 degrees Celsius to plus 400 degrees Celsius, while maintaining its mechanical and electrical insulating properties. These materials, layered together in blankets of 10 to 30 layers, depending on the application, create the thermal insulation systems that have protected spacecraft from the Apollo lunar missions to the James Webb Space Telescope on Voyager. The MLI blankets were carefully designed to cover every component that needed thermal protection, but they were also strategically interrupted at the locations of the thermal louvers and the radiators that allowed excess heat to escape during the warmer phases of the mission near the inner solar system. The engineering was not crude. It was precise thermal architecture, designed to maintain specific temperature windows across a mission profile that spanned from 1 astronomical unit to beyond the heliopause. 1 astronomical unit is the average distance from Earth to the Sun, approximately 149,597,871 kilometers. Voyager has now traveled more than 160 astronomical units from the Sun. The thermal environment at that distance is fundamentally different from anything accessible to ground-based testing. Engineers had to predict, using mathematical models and limited experimental data, how the spacecraft would behave across conditions. It would take decades to reach those predictions. Turned out to be remarkably accurate. Consider the challenge of designing a system in the 1960s and early 1970s that would function in 2026. Engineers had to account for material aging under cosmic radiation exposure. Cosmic rays, high-energy particles accelerated by supernova and other energetic events throughout the galaxy, penetrate spacecraft shielding and cause cumulative damage to electronic components. They ionize atoms within semiconductor devices, gradually altering the electrical characteristics of transistors and integrated circuits. They can also cause single-event upsets, where a single particle temporarily flips a bit in memory, corrupting data or causing a system malfunction. Voyager's electronic systems were designed with significant radiation hardening. The integrated circuits used were chosen for their resistance to radiation-induced damage. Redundant systems were incorporated for critical functions, so that if one component failed due to radiation damage, a backup could take over. These design choices, combined with careful power management and the lower radiation environment of interstellar space compared to the intense radiation belts around Jupiter, have allowed the spacecraft to continue functioning for far longer than its original design specifications required. Voyager was officially designed for a 5-year mission to Jupiter and Saturn. It has now operated for over 48 years. The mission was extended after the Saturn flyby because the spacecraft was still functioning well, and an extraordinary alignment of the outer planets presented an opportunity that would not recur for another 176 years. This alignment, sometimes called the Grand Tour, allowed a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune using gravity assists at each planet to continue to the next. Voyager 2 completed this grand tour. Voyager 1 was directed on a different trajectory that provided closer flybys of Saturn's moon Titan, ruling out the continuation to Uranus and Neptune, but enabling more detailed study of Titan's atmosphere. Gravity assist maneuver that propelled these spacecraft on their journeys is itself a remarkable feat of mathematical precision. A spacecraft approaching a planet in the right direction can steal a tiny amount of the planet's orbital momentum. The planet, being billions of times more massive, barely notices. The spacecraft accelerates significantly. Voyager 1's gravity assist at Saturn in 1980 boosted its velocity enough to send it on an escape trajectory from the solar system, permanently exiting the gravitational influence of the sun's pull. The mathematics required to calculate these trajectories to the necessary precision was performed on computers far less powerful than the smartphone in your pocket. The calculations were done largely by hand verification alongside early computer assistance, checked and rechecked by teams of scientists and engineers. The trajectories were designed not just to send the spacecraft past planets, but to time arrivals to coincide with optimal illumination conditions for photography, optimal positioning for atmospheric measurements, and optimal geometry for radio science experiments that used the spacecraft's radio signal to probe planetary atmospheres and rings as the spacecraft passed behind them. This is worth sitting with. The people who designed these trajectories had to predict with extreme precision where planets would be in space years into the future, had to calculate the gravitational effects of multiple massive bodies on the spacecraft's path simultaneously, and had to account for the tiny but cumulative effects of solar radiation pressure on the spacecraft's trajectory over millions of kilometers of travel. They got it right. They got it right with 1970s technology. They got it right well enough that Voyager 1 is still functioning today, still following a path that was calculated before the mission launched. The transmitter on Voyager 1 operates at a frequency of 8.4 gigahertz in the X-band microwave portion of the electromagnetic spectrum. The antenna is a parabolic dish 3.7 meters in diameter. It must be pointed with extraordinary precision at Earth for the signal to arrive with any detectable strength. Over interstellar distances, the transmitted signal spreads out in a cone. By the time it reaches Earth, the power of that signal has dropped by a factor of so many billions that the total power arriving at the receiver is approximately 10 to the power of minus 21 watts. That is 10 billion times smaller than the power required to light the LED indicator on a consumer electronics charger. The Deep Space Network, a system of large parabolic radio antennas operated by NASA at 3 locations around the world in California, Spain, and Australia, listens for Voyager's signal. The 3 sites are chosen to provide continuous coverage as Earth rotates, ensuring that at least one antenna is always facing in the direction of Voyager 1. The antennas are enormous by any measure. The largest dishes are 70 meters across, nearly as wide as a 23-story building is tall. They use cryogenically cooled receivers to reduce thermal noise to the absolute minimum, allowing them to detect signals at power levels that boggle the imagination. The data transmission rate from Voyager 1 is now approximately 40 bits per second. For reference, a low-resolution image on a modern website might contain several 100,000 bits. A single second of CD-quality audio contains 1,411,200 bits. Voyager's entire data rate is 40 bits per second. The spacecraft is essentially sending a trickle of information, a whisper across interstellar space. And we are listening with the most sensitive ears humanity has ever built. What does that trickle of information contain? Primarily measurements from the instruments still operating. The Plasma Wave Science Instrument, which measures electric and magnetic field oscillations in the interstellar medium. The magnetometer, which measures the direction and strength of the local magnetic field. And the low-energy charged particle detector, which counts energetic particles. These instruments provide a continuous, first-ever, direct measurement of the physical environment in the interstellar medium. Data that cannot be obtained any other way. The data Voyager 1 has sent back from interstellar space has already challenged some models of the heliosphere and the surrounding medium. For example, measurements of electron density in the interstellar medium have indicated higher densities than some models predicted. Observations of plasma oscillations have allowed scientists to indirectly measure the temperature and density of the surrounding medium in ways that ground-based observations of distant stars could not provide. Voyager is not just a traveler. It is, for a few more years at least, an active scientific instrument providing irreplaceable data. Understanding the boundary of our solar system matters for reasons beyond pure curiosity. The heliosphere provides the inner solar system with a degree of protection from galactic cosmic rays. If the heliosphere were smaller or weaker, cosmic ray bombardment at Earth's surface would be more intense. This has implications for biological evolution over geological timescales, for the long-term habitability of planets orbiting stars with weaker stellar winds, and for the design of future human missions to deep space. Astronauts traveling beyond the protective shield of Earth's magnetic field and the heliosphere face elevated radiation doses. Understanding the structure and dynamics of the heliosphere is therefore not purely academic. The question of what lies beyond the heliosphere is also deeply connected to the question of what our sun is moving through in the galaxy. The sun is not stationary. It orbits the center of the Milky Way at approximately 220 kilometers per second, taking approximately 225 to 250 million years to complete one orbit. As it moves, it passes through different regions of the interstellar medium. Some regions are denser and cooler. Some are hotter and more diffuse. Some may contain elevated concentrations of particular elements or isotopes. Our sun is currently moving through a region known as the local interstellar cloud, sometimes called the local fluff. This is a region of relatively warm, partially ionized gas, roughly 30 light-years across. Within the next 10,000 to 20,000 years, the sun may exit this region and enter a different interstellar environment. What that transition might mean for the size and shape of the heliosphere, and by extension for conditions in the inner solar system, is an active area of research. Data from Voyager 1 is directly relevant to understanding the properties of the medium at the current heliospheric boundary, looking further into the future of interstellar exploration. Voyager 1's journey has served as both inspiration and educational tool for the next generation of missions. Several proposed and in-development spacecraft concepts aim to follow and surpass Voyager. The interstellar probe concept, studied in detail by scientists at Johns Hopkins University Applied Physics Laboratory, under contract to NASA, envisions a spacecraft specifically designed for interstellar medium science. Unlike Voyager, which reached interstellar space almost by accident as a byproduct of planetary exploration, the interstellar probe would be designed from the start to cross the heliopause and operate in the interstellar medium for decades. Such a mission would use advanced RTG technology, potentially using americium-241 rather than plutonium-238, because americium-241 has a longer half-life of 432 years and could sustain power output for much longer missions. It would incorporate faster propulsion technologies to cross the heliopause within 15 years of launch, rather than the 55 years it took Voyager, allowing mission scientists to still be alive and professionally active when the spacecraft crosses the boundary. It would carry more advanced instruments than were possible with 1970s technology, and it would potentially include optical communication, systems capable of transmitting data at far higher rates than Voyager's radio. DOWNLINK. Advanced propulsion concepts discussed for such missions include solar sails, thin, reflective membranes that use the pressure of sunlight for acceleration, nuclear electric propulsion, where a nuclear reactor generates electricity that powers an ion drive, and laser-driven light sails, in which a powerful Earth or space-based laser array accelerates an ultra-lightweight probe to a fraction of the speed of light. The Breakthrough Starshot Initiative, funded by entrepreneur Yuri Milner and advised by scientists, including the late Stephen Hawking, has explored the concept of gram-scale probes accelerated by laser to 20% of the speed of light, capable of reaching Alpha Centauri within 20 years. Such probes would be unable to carry scientific instruments of any complexity, but they represent the extreme frontier of thinking about interstellar exploration. Voyager 1, by contrast, travels at less than 0.02% of the speed of light. The stars are very far away. But Voyager did something that none of these future concepts have yet done. It went. It is there. Right now, in interstellar space, a machine built by human hands is measuring the environment between the stars and reporting back. There is something worth examining in the specific combination of technologies that made this possible. The RTG technology that powers Voyager was developed starting in the late 1950s and first used in space in 1961. The SNAP-3 RTG flew aboard the Transit-4A Navy navigational satellite. Over the following decades, RTGs powered Apollo lunar surface experiments, the Viking Mars landers, the Pioneer spacecraft, and numerous classified military satellites. They became the established solution for powering spacecraft that travel too far from the sun for solar panels to work, and for powering instruments that require continuous operation, including through long planetary nights. The specific RTG design used on Voyager is called the multi-100-watt RTG. It uses silicon-germanium thermoelectric converters, which were the most efficient thermoelectric materials available at the time, converting approximately 6 to 7% of the thermal energy from plutonium decay into electricity. That conversion efficiency sounds low, but it was a significant improvement over earlier designs and represented the state-of-the-art in the 1970s. Modern RTG designs like the multi-mission radioisotope thermoelectric generator used on the Mars Science Laboratory mission and the Perseverance rover, use more advanced thermoelectric materials but still achieve conversion efficiencies in the range of 6 to 8%. The fundamental physics of thermoelectric conversion imposes limits. The Carnot efficiency limit, derived from thermodynamics, sets a theoretical maximum for any heat engine based on the ratio of the temperature difference between the hot and cold sides to the hot side temperature. For RTGs in interstellar space, where the cold side radiates to a medium near absolute zero, the theoretical maximum is high. But practical thermoelectric materials cannot approach that limit. Research into more efficient thermoelectric materials and conversion concepts continues, and future RTGs may achieve conversion efficiencies of 15% or higher. One often overlooked aspect of Voyager's survival is the robustness of its telecommunications system. The spacecraft uses a coherent transponder that can receive commands from Earth and transmit data back simultaneously. The receiver must lock onto an extraordinarily weak signal from Earth, distinguish it from background noise, decode the command sequence, and execute it. And this must work after decades of component aging, cosmic radiation exposure, and temperature cycling, as various systems have been powered down and then occasionally brought back up. In 2022, engineers discovered that Voyager 1 was sending garbled data from its attitude control system, the system that maintains the spacecraft's orientation and ensures the antenna points at Earth. The data appeared to be coming from a computer that was receiving commands from the main flight computer, but translating them into nonsensical binary before transmitting them back. Engineers diagnosed the problem over several months of analysis. The cause turned out to be a memory chip in the flight data system that had become corrupted, almost certainly due to decades of cosmic ray exposure. The solution required identifying exactly which bits of code were stored in the corrupted memory chip, figuring out how to move that code to a different region of memory without compromising the rest of the code, and sending the correction across 23 billion kilometers of space, with a round-trip communication time of over 44 hours. They did it. In April 2023, after months of careful work, Voyager 1 resumed sending coherent data. The 60-year-old engineers who had worked on the spacecraft in the 1970s and 80s consulted alongside newer team members who had spent their careers studying documentation written before they were born. The spacecraft's health was restored. This kind of event illustrates something profound about the nature of the Voyager mission and about human engineering at its finest. The spacecraft is so far away that any command takes more than 11 hours to reach it. Any response takes another 11 hours to come back. Every diagnostic procedure, every test, every code modification had to be thought through completely before transmission, because there was no possibility of an immediate back-and-forth conversation with the spacecraft. Engineers had to model exactly what the spacecraft would do in response to each command, predict the outcome, and be confident they had the right solution before they sent it. The current Voyager mission team is small. Fewer than 20 people actively maintain contact with Voyager 1 and Voyager 2. They know the spacecraft intimately, down to the individual component specifications of every system. Many of them have worked on the mission for decades. Some of the original Jet Propulsion Laboratory scientists and engineers from the 1970s still consult on the mission. There is a continuity of institutional knowledge that spans nearly half a century when Voyager finally goes silent. That knowledge will not disappear. It will be preserved in archives, in documentation, in the careers of scientists who worked on the mission and who taught the next generation. The mission has already inspired and informed decades of planetary science and heliospheric physics. It has provided data that has been cited in thousands of scientific papers. It has been the subject of books, documentaries, and countless educational programs. Its journey has been followed by space enthusiasts and scientists around the world. The golden record on board carries a message from the species that built Voyager. But in a sense, the spacecraft itself is a message. Every aspect of its engineering encodes knowledge. The RTG technology reveals our understanding of nuclear physics and materials science. The trajectory calculations reveal our mastery of orbital mechanics and gravitational dynamics. The telecommunications system reveals our understanding of electromagnetism and signal processing. The multi-layer insulation reveals our understanding of thermodynamics and materials engineering. The scientific instruments reveal what we thought was most important to measure about the solar system and the space beyond it. Voyager 1 will outlast every human institution that currently exists. It will outlast every language spoken on Earth today. It will outlast every country, every religion, every corporation, every government. In 40,000 years, when it makes its closest approach to Gliese 445, our civilization will have changed beyond recognition or ceased to exist entirely. But the spacecraft will still be there, frozen and silent, carrying its golden record past a dim, red star in a remote corner of the galaxy. It is the most durable artifact our species has ever created, not because it was built to last forever, but because the environment it inhabits applies no degradation forces. There is no oxygen to oxidize its metals. There is no moisture to corrode its circuits. There are cosmic rays slowly accumulating damage, but at such a slow rate that the structural integrity of the spacecraft may persist for millions of years. The gold-plated copper disk will survive essentially indefinitely. What comes next for interstellar exploration? The honest answer is that the gap between where we are and where we want to go is vast. No mission is currently funded or approved to specifically target the interstellar medium or beyond. The interstellar probe concept remains a proposal. Breakthrough Starshot remains in the research and development phase. The fundamental challenge of chemical and nuclear propulsion is that the energy required to accelerate a meaningful mass to speeds that would allow interstellar travel on human timescales is many orders of magnitude beyond what any current or near-term propulsion system can achieve. Science does not only advance through hardware. The data from Voyager continues to be analyzed. New findings emerge from archival data years after it was transmitted. Computer models of the heliosphere and the local interstellar medium continue to be refined using Voyager's measurements as ground truth. Every year, papers are published in journals like the Astrophysical Journal and Nature Astronomy that cite Voyager data in new analyses and new contexts. and the spacecraft is still transmitting, at least as of this moment, sometime in the late 2020s. The last active science instrument aboard Voyager 1 will no longer have sufficient electrical power to operate. The transmitter may hold on a little longer than the science instruments. Running on the last electrical power the dying RTGs can produce. And then that too will go quiet. The silence, when it comes, will be the end of something genuinely without precedent in human history. For over 50 years, humanity will have maintained contact with a machine that is farther from Earth than anything we have ever sent. Receiving data from a region of space that no sensor has ever previously measured. The silence will mark the end of an era in deep space exploration, but the spacecraft continues, silent, frozen, moving through the dark at 17 kilometers per second, carrying proof that a small, curious, briefly technical civilization once existed around a medium yellow star in one arm of a spiral galaxy among hundreds of billions of galaxies in a universe whose age is measured in billions of years and whose size exceeds our ability to meaningfully comprehend. Fact that we built this machine pointed it at the unknown, and it still works after nearly 50 years, is not merely a triumph of engineering. It is a statement about what is possible when a species takes seriously its desire to understand the universe it finds itself inhabiting. The cold of interstellar space did not defeat Voyager because the people who built it understood deeply and precisely what cold in space actually means. They understood radiation and conduction and thermoelectric conversion and radioactive decay and orbital mechanics and materials, science and thermal physics. They assembled that understanding into a machine the size of a small car and sent it on a journey that will last longer than human civilization has existed. Voyager 1 is still flying, and for a few more years, in the deepest silence imaginable, it will still be speaking. If this account of physics, engineering, and an extraordinary journey through the cosmos expanded your understanding of what cold in space actually means and what human ingenuity is capable of achieving, consider sharing it with someone who would find it as fascinating as you did. And keep watching the science, because the universe, as Voyager has so eloquently demonstrated, rewards those who pay close attention to fully appreciate how remarkable Voyager's survival is. It helps to understand just how precisely balanced the thermal engineering had to be, and how close some of those margins were to failing. The operational temperature range for the electronics aboard Voyager is approximately -40 degrees Celsius to +60 degrees Celsius. That range sounds generous, but maintaining it requires careful accounting of every watt produced and every watt lost over a mission spanning decades. When engineers designed the thermal system in the early 1970s, they had to predict the power output of the RTGs decades into the future. The rate at which heat would conduct through the spacecraft's structure, the emissivity of the spacecraft's exterior surfaces, and the amount of heat that would be generated by each electronic subsystem as it operated. Every one of those quantities changes over time. The RTG power output declines predictably as plutonium decays. The emissivity of surface coatings changes as they are exposed to ultraviolet radiation and cosmic rays in space. Electronic components age and their operating characteristics shift. The thermal analysis had to account for all of these changes across a mission duration that the engineers hoped would be 5 years, but that extended to decades. The fact that the spacecraft remained within operational temperature bounds across all of that time is a testament to both the quality of the original analysis and to the adaptive management controllers have applied over the decades. When specific components approached temperature limits, heaters were activated or deactivated. When power budgets grew tight, systems were prioritized and some were sacrificed to keep others running. The spacecraft was treated as a patient in intensive care, with constant monitoring and careful intervention to extend its functional life. It is also worth understanding what specific failure modes thermal engineers were designing against. Electronic components have minimum operating temperatures, below which their properties change in ways that prevent normal function. Capacitors, for example, change their capacitance at low temperatures. Some electrolytic capacitors will fail entirely if their electrolyte freezes. Transistors and integrated circuits slow down at low temperatures and can fail to meet timing specifications. Lubricants used in mechanical components like gyroscopes become too viscous at low temperatures to allow proper movement. Voyager contains a set of hydrazine thrusters used for attitude control, keeping the antenna pointed at Earth and maintaining the spacecraft's orientation for scientific measurements. These thrusters require liquid hydrazine propellant, which must be kept above its freezing point of approximately -2 degrees Celsius. Heaters maintain the propellant lines and thruster assemblies above this temperature. As the RTG power has declined, engineers have had to carefully balance the power allocated to propellant heating against the power required for science instruments and communications. In 2022, NASA made the difficult decision to shut off a heater serving the science boom on Voyager. That was keeping part of the spacecraft warmer than strictly necessary. In order to save power for science instruments, the component that was allowed to cool had been operating within specifications for decades, but was now operating outside its original design temperature range. The decision was made because the component appeared to be functioning normally despite the lower temperature, and because the alternative was losing scientific data from instruments that were providing unique interstellar medium measurements. These decisions are not made lightly. Each involves extensive analysis of how components have behaved in the current environment, predictions of how they will behave if temperatures continue to change, assessment of the risk of catastrophic failure against the benefit of continuing science operations, and review by teams of engineers and scientists. The mission team has developed an intimate understanding of how these 48-year-old spacecraft differ from their original specifications, and that understanding informs every decision. The plasma wave science instrument aboard Voyager 1 has been particularly productive in the interstellar medium. This instrument measures oscillations in the electric and magnetic fields of the surrounding plasma, called plasma waves. In the interstellar medium, the instrument has detected plasma oscillations that allowed scientists to measure the electron density of the local interstellar medium directly, without relying on models or indirect observations. These measurements showed that the electron density in the local interstellar medium near the heliopause is approximately 8 electrons per 100 cubic centimeters. Confirming and refining theoretical predictions, the instrument has also detected plasma oscillations associated with large solar events, specifically coronal mass ejections, the enormous eruptions of plasma and magnetic field from the Sun, even in interstellar space. More than 20 billion kilometers from Earth, the pressure wave from a particularly powerful coronal mass ejection can propagate outward and create detectable oscillations in the surrounding plasma. By measuring these oscillations, scientists can determine not only local plasma properties, but also track the propagation of solar activity effects into the interstellar medium. This is direct observational evidence of how our Sun influences its surrounding interstellar environment on scales never before directly measured. The magnetometer aboard Voyager 1 has provided continuous measurements of the interstellar magnetic field direction and strength. The interstellar magnetic field is not perfectly uniform. It has a preferred direction, flowing roughly parallel to the galactic plane, but it is turbulent on smaller scales. Voyager's measurements have shown that the magnetic field in the very local interstellar medium, the region just outside the helium, is organized in a way that is somewhat different from predictions based on observations of more distant regions. There appears to be a magnetic field draping effect at the heliopause, where the local interstellar magnetic field bends and aligns with the heliopause boundary. Rather than passing through it undeflected, these measurements have implications. 4 models of the heliosphere's shape and extent. The heliosphere is not a perfect sphere. The solar wind blows outward in all directions, but the Sun is also moving through the interstellar medium, creating a kind of bow wave effect. The upwind side, the direction the Sun is moving toward, has a compressed heliopause relatively closer to the Sun. The downwind side, trailing behind the Sun's motion, extends further. The exact shape and the role of the interstellar magnetic field in shaping it are topics of active research, and Voyager's data is central to those models. One of the surprises from Voyager 1's crossing of the heliopause was the observation that the heliospheric magnetic field and the local interstellar magnetic field were nearly aligned, within approximately 40 degrees of each other. This was not predicted by most models. It suggests that the interstellar magnetic field in our neighborhood is influencing the orientation of the heliosphere more strongly than previously assumed. Understanding this alignment is important because it affects how cosmic rays enter the heliosphere and how the solar wind interacts with the surrounding medium. Cosmic rays, the high-energy particles that Voyager's low-energy charged particle detector and cosmic ray subsystem instruments have measured, come from 2 primary sources. Galactic cosmic rays originate from supernova and other energetic events throughout the Milky Way and beyond. They are accelerated to extremely high energies by the expanding shock waves of supernova remnants and potentially by other mechanisms. Anomalous cosmic rays, a second population detected within the heliosphere, are believed to originate from neutral atoms in the interstellar medium that drift into the heliosphere, get ionized by solar radiation, and then are accelerated by processes at the termination shock, the inner boundary of the heliospheric sheath region called the heliosheath. Voyager 1's measurements showed that anomalous cosmic rays essentially disappear beyond the heliopause, consistent with the idea that they are produced within the heliosphere. Galactic cosmic rays, by contrast, are more intense outside the heliopause, consistent with the heliosphere, providing some shielding from them. The precise degree of shielding and how it varies with solar activity cycle are ongoing research questions. The termination shock is the inner boundary that Voyager 1 crossed in 2004, 8 years before crossing the heliopause. At the termination shock, the solar wind, which has been expanding outward and slowing as it moves away from the sun, abruptly slows to subsonic speeds as it encounters the resistance of the surrounding interstellar medium. This creates a shock wave, similar in concept to the sonic boom produced by a supersonic aircraft, where the solar wind transitions from supersonic to subsonic. The solar wind is compressed and heated as it crosses this boundary, and the region between the termination shock and the heliopause is called the heliosheath. The heliosheath surprised scientists. Models predicted it would be a fairly thin region of compressed solar wind, perhaps 1 billion kilometers thick. Voyager 1 spent approximately 8 years in the heliosheath before crossing the heliopause. The heliosheath was far thicker than expected, and it was more turbulent and complex than models had predicted. The magnetic field was tangled. The flow of solar wind particles was erratic rather than smooth. The transition to interstellar space at the heliopause itself was relatively sharp, a few 100,000 kilometers rather than billions of kilometers. These discoveries required revisions to heliospheric models. The shape of the heliosphere, the dynamics of the heliosheath, and the structure of the heliopause boundary are all areas where Voyager data forced a rethinking of theoretical assumptions. This is what good science looks like. Observations that challenge existing models and force more accurate understanding. The science of heliospheric physics has an entire branch of space physics and astrophysics devoted to it. Scientists study the heliosphere not only because it is our home environment in the galaxy, but because it is a laboratory for understanding how stellar winds interact with the interstellar medium in general. Every star with a stellar wind creates its own astrosphere, the stellar equivalent of our heliosphere. Understanding our own heliosphere in detail gives us a template for understanding the environment around other stars, which has implications for the habitability of planets around those stars, particularly in terms of cosmic ray shielding and the protection of planetary atmospheres. Mars, for example, lost most of its atmosphere billions of years ago. The reasons are complex and still debated. But one factor is that Mars lost its global magnetic field early in its history, which reduced the protection it received from both solar wind particle stripping of the upper atmosphere and cosmic ray bombardment. Earth's strong magnetic field deflects most of the solar wind around the planet, creating the magnetosphere, which in turn is embedded within the heliosphere. The layered protection of magnetosphere plus heliosphere is part of what makes Earth habitable over geological timescales. On very long timescales, changes in the heliosphere could affect conditions on Earth when the Sun passes through denser regions of the interstellar medium. The heliopause may compress inward, reducing the heliosphere's volume and potentially allowing more galactic cosmic rays to penetrate to the inner solar system. This has been proposed as a possible contributing factor to some mass extinction events in Earth's history, though the evidence remains debated. Compelling given the many other factors influencing biodiversity. The Voyager mission has contributed observational evidence that helps constrain these models by measuring the properties of the local interstellar medium directly. Voyager provides a reference point for what conditions are like in our current galactic neighborhood. Future missions that can probe a wider range of distances and directions from the Sun will build on this foundation. It is also worth reflecting on what Voyager 1's mission has told us about the nature of scientific planning and the unexpected dividends of fundamental research. When the Voyager missions were designed, the primary scientific goals were to study the planets of the outer solar system, Jupiter, Saturn, and in the case of Voyager 2, Uranus and Neptune. The planetary flybys were the headlines. The scientific discoveries at Jupiter alone would have justified the entire mission cost many times over. The active volcanism of Io, the complex ring system of Saturn, the varied geology of the Jovian and Saturnian moons, all of these were headline discoveries. The interstellar mission was almost an afterthought in the original conception. The spacecraft would continue operating after the planetary encounters. Yes, and it would eventually reach the edge of the heliosphere. But no one in 1977 knew precisely when that would happen, what the boundary would look like, or what the interstellar medium would be like on the other side. The instruments that have proven most valuable for interstellar medium science were designed primarily for planetary magnetosphere and plasma science. They happened to still be working 40 years later when the spacecraft reached the Jalapa USE. This is a recurring pattern in the history of space exploration. The Hubble Space Telescope, launched in 1990 with optical instruments optimized for observing galaxies and distant objects, has contributed enormously to solar system science, including detailed studies of planetary atmospheres, comets, and even Pluto. The Cassini spacecraft, sent to orbit Saturn for 4 years, ultimately orbited for 13 years and made discoveries ranging from the geysers of Enceladus to the detailed chemistry of Titan's atmosphere. The Curiosity rover on Mars, designed for a primary mission of 2 years, is still operating after more than 13 years on the Martian surface, planning for long-duration scientific missions requires building spacecraft that can outlast their original specifications, and it requires maintaining the institutional knowledge and team continuity to take advantage of that longevity. Both NASA and the broader scientific community have learned this lesson repeatedly from Voyager and other long-duration missions. The science that comes from the extended phases of these missions is often as valuable as the primary mission science, precisely because it is science that was not anticipated and that addresses questions that were not even well formulated when the spacecraft launched. Voyager 1 was also the first spacecraft to perform detailed studies of the Jovian magnetosphere, the enormous magnetic field bubble that Jupiter projects into space. Jupiter's magnetosphere is the largest structure in the solar system, extending far beyond the orbit of Saturn on the sunward side and stretching into a magnetale, extending hundreds of millions of kilometers in the downwind direction. It is so large that if it were visible to the naked eye from Earth, it would appear larger than the full moon in the sky. The Voyager observations of Jupiter's magnetosphere revealed a complex, dynamic system with intense radiation belts, a plasma torus associated with Io's volcanic emissions, and complex magnetic field structures that have been studied in detail by every subsequent mission to Jupiter and Saturn. Voyager provided the first detailed images and measurements of the ring system, revealing far more complexity and structure than had been observed from Earth. The rings contain hundreds of distinct ringlets, gaps, and waves. Some of these features are associated with orbital resonances with Saturn's moons. Some are caused by small embedded moonlets that act as shepherds, maintaining sharp ring edges. Some remain unexplained decades later. The Cassini mission, which arrived at Saturn in 2004 and orbited for 13 years, answered many of the questions Voyager raised and asked many new ones. Voyager's flyby of Titan, Saturn's largest moon, was one of the mission's most scientifically significant moments, even though it was scientifically frustrating at the time. Titan has a thick atmosphere of nitrogen and organic compounds that is completely opaque to visible light. Voyager's cameras could not see the surface through the haze. Scientists could measure the atmosphere's composition and temperature profile, establishing that Titan had a surface pressure slightly greater than Earth's and that methane was abundant in its atmosphere. But they could not see what lay beneath the clouds. The Huygens probe, released by Cassini and descending through Titan's atmosphere in January 2005, revealed a world with liquid methane lakes, river channels carved by methane rainfall, an organic chemistry of extraordinary complexity. The basic curiosity generated by Voyager's frustrating inability to see through Titan's atmosphere directly motivated much of the scientific case for the Cassini-Huygens mission. Voyager showed us enough to know that Titan was extraordinary. Cassini-Huygens showed us why. The legacy of Voyager extends far beyond the data it transmitted. It extends into the entire discipline of planetary science, into the careers of thousands of scientists who were inspired by the mission's images and discoveries, into the engineering approaches used in every subsequent outer solar system spacecraft, and into the public understanding of the solar system and our place within it when Voyager 1 finally goes silent. Some of those who built it, some of the scientists who analyzed its early data are still publishing research today. There is a human continuity to this mission that transcends the spacecraft itself. The knowledge it has generated, the scientific papers, the textbooks it has informed, the images that have become iconic. The concept of the pale blue dot that Carl Sagan used when he persuaded NASA to turn Voyager's cameras back toward Earth in 1994, a final portrait of our home planet from 6 billion kilometers away. That continuity is the most durable part of the legacy. In the 1990 pale blue dot image, Earth appears as a tiny fraction of a pixel, a mote of dust suspended in a sunbeam, as Sagan described it. The image became the basis for one of the most celebrated scientific meditations ever written, Sagan's reflection on the apparent insignificance of our planet and the corresponding importance of treating it and each other with care. That image, made possible by Voyager 1's existence and its trajectory, has been shared billions of times and has influenced how countless people think about the scale of the universe and the value of the planet we share. It was not a scientific measurement in the traditional sense. It produced no data that advanced heliospheric physics or planetary science. But it may have been the single most impactful thing Voyager ever transmitted, precisely because it showed us ourselves from a perspective no human had ever had before. The question of what to do after Voyager goes silent. What mission or missions should carry the torch of outer solar system and interstellar exploration into the coming decades is one that the scientific community has been debating and planning for some time. The National Academies of Sciences, Engineering, and Medicine publishes a prioritized list of planetary science missions called the Decadal Survey every 10 years. The most recent survey, published in 2022 for the period 2023 through 2032, prioritized a Uranus orbiter as the top flagship mission for the next decade. Uranus is the only gas giant in the solar system never to have been visited. Voyager 2's flyby in 1986 lasted only a few hours. A dedicated orbiter mission could provide the kind of detailed, long-duration observations that revolutionized understanding of Jupiter and Saturn through the Galileo and Cassini missions, respectively. Beyond Uranus, the community continues to discuss the interstellar probe concept, Neptune and Triton missions, continued study of the ice giants and their moons, and the question of sending a mission specifically designed to probe the interstellar medium at and beyond the heliopause. The scientific case for each of these missions is strong. The budget constraints are significant. Choices will have to be made. Whatever comes next, it will be informed by what Voyager 1 and Voyager 2 have taught us. The thermal engineering approaches, the RTG technology, the telecommunications architecture, the trajectory planning methods, all of these have a direct lineage from Voyager. Every spacecraft that has operated in the outer solar system since, from Galileo at Jupiter to Cassini at Saturn to New Horizons at Pluto and the Kuiper Belt, carries the inheritance of lessons learned from Voyager. There is something quietly extraordinary about a machine built with 1970s technology, a time before personal computers existed, before the internet existed, before GPS navigation existed, operating in interstellar space in 2026. The world in which Voyager was designed is as foreign to us now as the world of the early 20th century seemed to people in the 1970s. And yet the physics that the engineers applied, the mathematics of orbital mechanics, the thermodynamics of heat transfer, the nuclear physics of radioactive decay, those are unchanged. The laws of nature do not update with the decades. That is the deepest lesson in Voyager 1's survival. The cold of interstellar space is not defeated by clever tricks or technological magic. It is defeated by a precise, deep, and mathematically rigorous understanding of how heat behaves when there is almost nothing around to carry it. By understanding that conduction requires matter and matter is absent, by understanding that radiation is slow and manageable, by engineering a power source whose output is governed by a physical law, the law of radioactive decay that cannot be circumvented or interrupted, by insulating against radiative loss with the best materials available, and by designing the entire system with sufficient margin that it could be managed and maintained over a mission timeline far longer than anyone officially planned for. Voyager did not survive by luck. It survived because the people who built it understood the universe well enough to design something that could live in the harshest part of it we have ever reached. That is not a small thing. That is perhaps the most impressive achievement in the history of human engineering. measured not by the sophistication of the technology, but by the depth of understanding required to make something so simple, so elegant, and so durable. The spacecraft is still out there. Right now, as these words are read or spoken, Voyager 1 is adding another 17 kilometers to its distance from the Sun with every passing second. It is crossing a region of space no instrument has mapped before. It is measuring a medium no probe has previously sampled, and it is still, for a little while longer, sending those measurements home. When the silence finally comes, it will mark the end of a specific era, but the knowledge it carried home, encoded in electromagnetic signals traveling at the speed of light across 23 billion kilometers of empty space, is already here, already stored, already woven into our understanding of the heliosphere, the interstellar medium, and the solar system we inhabit. The final signal has not yet been sent. There is still time to listen. There is a dimension of Voyager 1's story that has received less attention than the engineering achievements and the scientific discoveries. And it concerns the nature of what it means to build something meant to outlast your own civilization. The engineers and scientists who designed Voyager 1 were, almost to a person, aware of the extraordinary timescales involved. A spacecraft escaping the solar system will travel through interstellar space for longer than Homo sapiens has existed. The golden record was included not because anyone seriously expected it to be found, but because it felt appropriate to acknowledge the magnitude of what was being attempted. You do not send the first human-made object into interstellar space without at least trying to introduce yourself. Carl Sagan, who chaired the committee that selected the content for the golden record, described the feeling as being like casting a message in a bottle into the cosmic ocean. The bottle will drift for eons. The civilization that cast it will not be there to see if it is ever found. The act of including the record was as much a statement about the people who made it as it was a message to any hypothetical recipient. The golden record includes greetings in human voices, speaking 55 different languages, beginning with Sumerian and including every major language family on Earth at the time of launch. It includes mathematical and physical notation intended to allow a technically sophisticated recipient to decode the rest. It includes images of humans at various stages of life. It includes music spanning cultures and millennia, from Beethoven's Fifth Symphony to a Azerbaijani folk music to a Pygmy Girls initiation song to Chuck Berry's Johnny Be Good. The choice of what to include and what to exclude from the golden record was the subject of considerable debate. Some selections were made on aesthetic grounds. Some were made to represent the diversity of human culture. Some were made because they were considered the most likely to be aesthetically meaningful to an intelligence with very different sensory systems than ours. The record contains no images of war or conflict, not because the committee wanted to deceive any finder about the nature of human civilization, but because they wanted the record to emphasize what humanity aspires to be rather than what it too often is. The record itself is made of gold-plated copper, chosen for durability. It is accompanied by a cartridge and needle for playback, with a diagram on the cover showing how to use it, along with a pulsar map giving the position of Earth relative to 14 radio pulsars and the galactic center. Information that would allow any sufficiently advanced civilization to locate the Sun. The map is the same pulsar map used on the Pioneer plaques, which flew on Pioneer 10 and Pioneer 11, the first spacecraft to escape the solar system. Launched in 1972 and 1973, both Pioneer spacecraft are now also in interstellar space, ahead of the Voyagers in their respective directions of travel. Pioneer 10 was the first spacecraft to cross the heliopause, though we have no confirmation of exactly when this occurred, because Pioneer 10's transmitters went silent in 2003. Before the crossing could be confirmed by the measurements that Voyager 1 later made, Pioneer 11 went silent in 1995. They carry their plaques into the interstellar medium, silent and frozen, as Voyager will carry its golden record. The 4 spacecraft, Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2, are humanity's first 4 emissaries into interstellar space. Each went in a different direction, driven by the different trajectories of their planetary flybys. Voyager 1 heads toward the constellation Ophiuchus, roughly in the direction of the solar apex, the direction the Sun is moving toward as it orbits the galaxy. Voyager 2 heads toward the constellation Telescopium in the southern celestial hemisphere. Pioneer 10 heads toward the constellation Taurus. Pioneer 11 heads toward Aquila. Together, they point in 4 very different directions into the galaxy. 4 messages launched at roughly the same moment of human civilization, diverging forever. No alien civilization has contacted us regarding these spacecraft. No signal has been received that would indicate detection. This is not surprising. The distances involved and the time required for any return signal to reach us make any response, under even the most optimistic assumptions about the prevalence and technological capability of other civilizations, highly unlikely within any human-relevant time frame. But the spacecraft were not sent expecting a reply. They were sent because sending them was an expression of who we are. There is a concept in philosophy and theology, sometimes called a monument to the transcendent. The idea that some human creations are attempts to reach beyond the ordinary scale of human time and effort, to make something that participates in eternity. Cathedrals, ancient obelisks, and the pyramids of Giza are often cited as examples. They were built to last far beyond the lives of their creators, to carry meaning forward across centuries and millennia. The Voyager probes are, in a secular scientific sense, a version of this impulse. They are the first human artifacts to participate in interstellar. They will outlast every other human creation. They will be out there long after the Earth itself has been rendered uninhabitable by the expanding Sun in approximately 5 billion years. The Sun is currently in the middle of its main sequence life. It has been burning hydrogen into helium in its core for approximately 4.6 billion years and has approximately another 5 billion years of main sequence life ahead. As it ages, it will gradually brighten and expand. Within approximately 1 billion years, the increased solar luminosity may make conditions on Earth too warm for liquid water to persist on the surface. Within 5 billion years, the Sun will expand into a red giant, consuming the inner solar system, potentially including Earth by then. All traces of human civilization on Earth will long since have been erased by geological processes, plate tectonics, erosion, and solar heating. But the Voyager spacecraft, drifting silently through interstellar space, tens of billions of kilometers from the now red giant sun, will still be out there. The frozen, silent machines will have outlasted every other physical trace of the civilization that built them. This is not meant to be melancholy. It is simply an acknowledgement of the scales involved when you send something truly beyond the solar system. Voyager 1 was built to be thrown, and it was thrown hard, and it will travel for longer than we can imagine. The machines we build to explore the universe turn out to be more durable than the civilizations that build them. That thought is not a reason for despair. It is a reason for wonder. The Voyager program spent approximately $865 million across both spacecraft over several decades of development and operation. Adjusted for inflation, a figure in the billions of dollars by modern standards. But an extraordinarily modest investment for what it returned. The scientific discoveries alone, the revelations about the outer solar system, the first direct measurements of the heliosphere's boundaries, the ongoing interstellar medium data would justify many times the cost. The cultural impact, the images, the golden record, the pale blue dot, the simple fact that humanity reached interstellar space with machinery built in the 1970s is incalculable. The people who built Voyager 1 are mostly retired or gone, but the spacecraft is still flying. Every day, it adds about 1.47 million kilometers to its distance from Earth. Every day, it carries a tiny piece of human civilization a little further into the galaxy. And for a few more years, every day, it sends us back a trickle of measurements. 40 bits per second from a place no one has ever been. We are listening. We are still listening. And we will keep listening until the last signal fades. That is enough. That is more than enough. It is, by any measure of what our species is capable of, at its best, extraordinary. So the next time someone asks you why Voyager 1 has not frozen after nearly 50 years in interstellar space, you have a complete answer. Cold in space does not work the way cold works on Earth. Heat cannot conduct when there is almost nothing to carry it. Radiation is slow. A heartbeat of decaying plutonium generates enough warmth to sustain electronics for decades. The best insulation ever engineered holds that warmth in, and the result, a spacecraft smaller than a school bus, running on less electricity than a household lamp, has survived conditions that would destroy almost everything else humanity has ever built. The universe is extreme. So was the engineering. And somehow, against every reasonable expectation, it worked.